All right, chapter 6, we're starting with linear programming, the simplex method, looking at the table method. And it's an introduction to what's called the simplex method. That's what we're going to do next week. And it's going to involve matrices. Okay, the table method, an introduction. This section will introduce the table method to solve linear programming problems without the necessity of drawing a graph of the feasible region. You guys didn't like doing that very much, apparently. Okay, so standard maximization problems in standard form. A linear programming problem is said to be a standard maximization problem in standard form if, okay, so you're wanting to put it in standard form. The objective function, this one up here, has to be maximized, not minimized. You have to be maximizing. Okay, you have to be maximizing the objective function. Second thing, all constraints involve a less than or equal to and have positive constants to the right of the inequality. All of these numbers over here on the right side of the inequalities have to be positive. All of the inequalities have to be less than or equal to. And the third thing's all variables are non-negative, meaning this last line. Got it? All right, the example. This is in standard form. It says to maximize the objective function. It has less than or equal to's in the constraints. It has positive numbers on the right of the inequalities, and all of the variables are non-negative. Got it? All right, we're going to introduce what are called slack variables. If you'll notice, this involves inequalities, right? It's called the I system, indicating inequalities. When we introduce what are called slack variables, we're going to come up with the E system, which stands for equations. So here we go, slack variables. To adapt a linear programming problem to the matrix methods used in the simplex method, which is next week, we must convert the problem constraint inequalities into a system of linear equations. We're going to convert inequalities to equations, all right, by introducing what are called slack variables. That first inequality up here says x1 plus 2x2 less than or equal to 32. Okay, x1 plus 2x2 and 32. You had a less than or equal to, right? But if I add what's called a slack variable, I can change it into an equation. Because you have this value plus something else will give you positive 32. For this, doing it the same way for the second inequality down here, you're going to say 3x1 plus 4x2. In order to get equals 84, you've got to introduce a second slack variable. So for each inequality, you introduce a slack variable and turn it into an equation. Got it? All right. Definition. The variables S1 and S2, what are they called? They're called slack variables. Because each makes up the difference or takes up the slack between the left and the right sides of the inequality system. Okay, notice when you introduced slack variables, it turned it into an E system because there are equations. All right, you start with an I system. You've got to make sure it's in standard form. Then you introduce slack variables and turn it into an E system. We're good on how to do that. All right, notice if x1 is 20 and x2 is 5, so we're looking right here. If x1 is 20 and x2 is 5, what would S1 be? What would the slack variable have to be? So you would end up with 20 plus 2 times 5 plus S1 equals 32. 20 plus 10 is 30. So S1 would be 2. All right. If the decision variables x1 and x2 satisfy the system of constraint inequalities, then the slack variables S1 and S2 have to be non-negative. Let's read that again. If x1 and x2 satisfy the inequalities, then your slack variables have to be non-negative. So here in a minute, we're going to do a table, and if any of our slack variables turn out to be negative, we're going to cross it out. We're going to cross that whole row out because it can't be a solution of the inequality system. Got it? All right. The table method, the setup. The solutions of the I system are points in the feasible region. You remember when we did it the graphical way? All of these points in here satisfied the inequalities. It satisfied the constraints. That's how we got the feasible region. We graphed all the inequalities and took the intersection. Okay, for example, the coordinate 20, 4, where is that? 20, would be about right here. That's not a very good point. Right here. That point is a solution, right? But the point 20, 8, which would be up here, is that a solution of the inequality system? No, because it's not in the feasible region. So all of these points in here would be solutions. We good there? All right. The solutions of the E system. Wait a minute. What does E system mean? The E system is when you've introduced the slack variables and turned the inequalities into equations. Okay, the solutions of the E system are quadruplets. Quad meaning 4. You have to have a value for your two variables, x1 and x2, and for your two slack variables, s1 and s2. So the solutions of the E system are quadruplets. The quadruplets are called the expanded coordinates. For example, the quadruplet 20, 4, 4, 8, and the quadruplet 28, -4, -8 are solutions. So both of those quadruplets would be solutions to the E system. Okay, the I system and the E system do not have the same solutions. The solutions to the I system have, they're ordered pairs, and the solutions to the E system are quadruplets. All right, however, the solutions of the I system correspond to the solutions of the E system, in which the variables x1, x2, s1, and s2 are all non-negative. Remember that thing on the last page? S1 and S2 had to be non-negative. All right, so that's important. They've said it twice. A solution of the E system in which the values of all decision variables and slack variables are non-negative is called a feasible solution. Why is this one not feasible? The slack variables are negative. You cannot have negative slack variables. All right, by looking at line segments that form a boundary for the feasible region, we conclude that for any corner point P of the feasible region, okay, wait a minute, corner points. The corner points would be here, 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 and there. Those are the corner points, right? All right. For any corner point of the feasible region, at least two of the variables must equal 0 in the expanded coordinates of P. At least two of the variables must equal 0. So when you have your quadruplet, two of them have to be 0. The trick is finding which two it should be. Okay, the table method with two decision variables. Assume that a standard maximization problem in standard form has two decision variables, x1 and x2. Two decision variables, x1 and x2. And it has m constraints. So those are the inequalities, right? Okay, step 1, use slack variables to convert from the I system to the E system. Okay, we're going to convert. Step 2, form a table. All right, here's the trick. This many rows and this many columns. Rows go across, columns go up and down. All right, in the first row, you're going to assign 0 to x1 and x2. In the second row, you're going to assign 0 to x1 and s1. And you're going to continue until all the rows contain all possible combinations of assigning 2 zeros to the two variables. What does that look like? I'm going to jump down to a table. Do you see the columns up here have the two decision variables, x1 and x2, and then all the slack variables? How many constraints were there on that problem? How many constraints, how many inequalities were there? 2. How do you know that? Because there's 2 slack variables. Exactly. All right. The procedure that was just described, do you see that you see x1 and x2 are both 0? Then you let x1 and s1 be 0. Then you let x1 and s2 be 0. That's all the ways, all the combinations if you had 0 for x1. Okay, now move over to x2. You've already got x2 and x1. So now you need to do x2 and s1, x2 and s2. Then you move over again and let s1 and s2 be 0. That's all the different combinations of putting 2 zeros on each row. All right. We know how to set the table up. Oh, the number of rows and the number of columns. If there were 2 constraints, so down here on that problem, If there are two constraints, how many rows would you have? 2 plus 2 is 4, times 2 plus 1 is 3 over 2. You'd have 6 rows. I'm using that formula. How many columns would you have? You'd have 2 plus 2, which is 4 columns. Okay? All right. Step 3. Complete each row to a solution of the E system if possible. Because 2 of the variables have the value 0, this involves solving a system of m linear equations in m variables. Back to the good old Gauss-Jordan, RREF method. If the system has no solution or infinitely many solutions, don't complete that row. All right, step 4, find the maximum value of P over those completed rows that have no negative values. If you get a negative value for a slack variable, what are you going to do to the row? Cross it out. Okay, if the optimal value of the objective function, it is the optimal value of the objective function provided the optimal value exists. All right, here we go. We're going to actually go set up the table and solve that table for this initial problem that we were given. All right, this is the I system, right? I'm going to get rid of that. We need to convert it to an E system. You remember how? Slack variables. So I'm going to say x1, 2x2 plus a slack variable equals 32. You with me? I'm going to say 3x1, 4x2. Can I say plus s1? I've got to do a new slack variable. I'm going to say plus s2 equals 84. This is the E system. I have 2 constraints. So my M is 2. And we already did this up here. We found that we have 6 rows and 4 columns, correct? M is 2. All right, I did a table. I put my variables up top across the headers of the columns. I'm supposed to have 6 rows. 1, 2, 3, 4, 5, 6. Good. Then we went and assigned zeros in 2 spots per row, right? Now we need to go solve the system. We need to go fill in the table. Okay, cleaning this up a little bit. If I let x1 and x2 be 0, I'm going up here to the E system. If x1 and x2 are both 0, those go away, right? Oh, yeah, I'm looking at the answer. S1 would be 32 and S2 would be 84. Well, that's an easy row to do. You good? Row 2. Oops. Okay, here comes row 2. X1 and S1 are 0. Okay, so here's row 2. X1s are 0 and S1 is 0. So what's my system going to look like? 2x2 equals 32. 4x2 plus s2 is 84. You can solve this by hand if you want to. What would x2 be? X2 would be 16. If x2 is 6, oh, sorry, x2, not s2. x2 is 16. If x2 is 16, then 4 times 16 plus s2 would be 84. So, what is that? Don't make me do arithmetic. 4 times 16, 64. And then we want to do 84 minus 64. Perfect. That's 20. Now, I would not choose to do it that way. I don't like doing any arithmetic by hand if I can get away with it. Do you see that we could put that in a matrix and do 2, 0, 32, 4, 1, 84, and you can go RREF it. Now, how many RREFs are we going to have to do? 4 more of them. That's easier than doing the whole graphing thing, right? Well, if you say so. All right. So if you chose to do it the RREF way, you would have seen 1001 1620. All right, go set up the matrix for the third row for this one. How would you do it? Those would be 0, and S2 would be 0. So your matrix would be 2, 1, 32, 2, 1, 32, and 4, 0, 84. You would go RREF that one. You see the process? It takes a while. You would get, in the end, I'm going to get rid of all this and show you what you would come up with. Okay, the rest of your solutions would be, let's see here, 21, negative 10, 32, come on, and negative 12, and then 28, 4, 26. Anytime the slack variables were negative, what do you do? Okay, I see a negative there and a negative there. I'm going to go cross out that entire row. Okay. This is what you would put down here. The only difference, the table on that next page contains one more column for the optimal, the function you're supposed to optimize. Yep. So back to here. I'm going to give you time to copy that down. The only difference between that table and this table is this. You need to go maximize it. So here we go. P equals 50x1 plus 80x2. When you plug in 0 for x1 and 0 for x2, what is your P? 0. If you plug in 0 for x1 and 16 for x2, I'm just looking at these two columns. If I plug in 0 for x1 and 16 for x2, what's 80 times 16? 1,280. Do I need to plug anything in for rows 3 and 4? No, because I had a negative slack variable. For row 5, if I plug 28 for x1 and 0 for x2, 50 times 28 is 1,400. Then if I plug in 20 for x1 and 6 for x2, I would do 50 times 20 plus 80 times 6. Okay, which one is the maximum value? The very last one. The solution to this system, to this linear programming problem, would be x1 is 20, x2 is 6. The maximum value of the objective function p would be 1480. Okay, so going down, let's see if we've answered everything. Okay, the solutions in rows 1, 2, 5, and 6. That was where the slack variables were not negative. Those are called basic feasible solutions. It just depends. Just depends. They correspond to the corner points of the feasible region. Oh, wait a minute. You mean those things are these corner points over here? They correspond to those 4 corner points? Okay. There's a theorem. If the optimal value of the objective function in a linear programming problem exists, then that value must occur at one or more of the basic feasible solutions. Cool.